Pull it tight.
Holding steady.
Secure the risers now.
These figures confirm our fears. We don't have enough rifles to arm the incoming division.
Exactly, sir. If we don't reroute supplies immediately, we won't hold the line.
How many in this batch?
50, sir. All checked.
Right. Get it labeled fragile silk only and loaded immediately.
January 1941. A cold morning grips Wilmington, Delaware. Frost clings to the windows of DuPont's sprawling research labs. Inside, the air hums with quiet tension. Engineers in white coats lean over rows of gleaming machinery, their breath fogging in the chill as they inspect strands of a strange, golden fiber. This is nylon, America's first fully synthetic polymer, still fragile, still untested under the weight of a human life. Outside, on a windswept field, a small group of uniformed paratroopers crouches beside canvas and cord. They watch as a test rig lifts a nylon chute skyward, the fabric catching the pale winter sun. The soldiers exchange uneasy glances. Silk, imported from Asia, had been the only material strong enough for parachutes, but supply lines were precarious, and a war was spreading. Now, the country's hope rests on this new invention. In the lab, Wallace Carruthers' team adjusts tension and weave, hands shaking slightly, aware that every failure could cost lives. Across the field, the first nylon chute flutters downward, holding its shape. The soldier's eyes widen. It works, but only just. The war waits for no one. And soon, nylon would have to save thousands of lives. By the winter of 1940, the world was already engulfed in flames. Europe had fallen into chaos. Germany's blitzkrieg had overrun Poland, France, and much of the Low Countries. Across the Atlantic, the United States watched with growing unease, still officially neutral, but increasingly aware that global conflict would soon reach its shores. The U.S. military faced a sobering reality. While Europe waged war with modern armies, America's forces were underprepared. Equipment shortages were rampant. One problem, seemingly small but critically important, loomed large. The nation had no synthetic fibers capable of replacing silk. Parachutes, essential for airborne operations and supply drops, depended entirely on silk imported from Asia. Japan's expansion in China and its growing hostility in the Pacific made these supply lines increasingly precarious. Every silk shipment carried the risk of delay, interception, or confiscation. Enter DuPont, a chemical giant whose laboratories had already begun pioneering new polymers in the 1930s. Under the direction of Wallace Carruthers, a meticulous chemist, DuPont had been experimenting with synthetic fibers for years. Carruthers' team sought something that could mimic the strength of silk while offering unprecedented elasticity and resilience. Early experiments produced fibers that snapped easily or tangled beyond repair. Yet the urgency of war injected a new intensity into their work. Scientists worked long nights, testing chemical formulas, weaving threads by hand, and running repeated stress tests. Military officials, Meanwhile, pressed for results, the U.S. Army's Quartermaster Corps had begun compiling reports on parachute failures. Silk parachutes, though reliable in theory, were limited in quantity. Training jumps were curtailed. Pilots and paratroopers practiced on worn-out chutes, their lives tethered to imported threads over which the government had no control. The Army understood that a single innovation could tip the scales, a synthetic fiber strong enough to bear a human's weight, light enough to be packed efficiently, and abundant enough to equip thousands of soldiers. DuPont's labs became a pressure cooker of scientific and military expectations. Each test failure was not just a setback in the lab. It was a potential battlefield casualty waiting to happen. Researchers recorded tensile strengths, stretch percentages, and environmental resilience with painstaking care. Notes scribbled in logbooks detailed fiber behavior under wind, heat, and moisture. Every detail mattered. The consequences of error were life or death. The American textile industry was itself unprepared. Natural fibers like cotton and wool were abundant, but they lacked the combination of strength, elasticity, and lightness required for parachutes. Nylon promised a revolution. A synthetic polymer that could be spun into threads fine as hair, but strong enough to carry a fully equipped soldier safely to the ground. The concept was audacious, but necessity made it urgent. By early 1941, the laboratory's experiments were no longer theoretical. Nylon fibers had begun to meet minimum strength requirements. The Army requested small-scale prototypes. Volunteers, often young engineers and lab assistants, subjected the threads to rigorous stress tests, simulating the weight of a fully geared paratrooper. In nearby testing fields, parachutes were fitted to sandbags and dropped from low heights, gradually increasing in scale. Engineers watched each descent with bated breath. Every flutter of fabric could signal success or catastrophic failure. Beyond the laboratories, DuPont faced industrial challenges. Scaling production from a few experimental strands to hundreds of thousands of yards required precision machinery, skilled labor, and vast quantities of raw chemicals. Every spool of nylon had to be identical. Any inconsistency could compromise the parachute's integrity. The company retooled entire sections of its factories, trained workers to handle the delicate fibers, and established quality controls that were unprecedented in textile production. This backdrop, global war, military urgency, and industrial innovation, set the stage for a critical question. Could nylon succeed where silk had dominated for centuries? The answer would determine not only the safety of paratroopers, but also America's readiness to engage in modern warfare. And as DuPont's engineers prepared the first full-scale prototypes, a looming shadow hovered over the project. Would a new synthetic fiber be ready in time to save lives on the battlefield? The fate of thousands would hinge on the answer. As 1941 began, the U.S. military faced not just shortages, but stark technical requirements. A parachute was not merely a bundle of fabric. It was a lifeline. Each canopy had to absorb the weight of a fully equipped soldier, withstand sudden gusts of wind, and deploy reliably from hundreds of feet above the ground. Silk, the traditional material, had served well for decades, but its availability was dwindling. The Army needed a fiber that could do more and do it consistently. DuPont's engineers began experimenting with large-scale spinning of nylon threads, carefully controlling the chemical processes that gave the fiber its strength. The first industrial attempts were fraught with failure. Threads snapped under tension. Weaves refused to hold shape. Nylon had the potential to exceed silk's capabilities, but it required perfect alignment of polymers and precise weaving techniques. Small errors could render a parachute useless. Each setback intensified the pressure, both in the lab and for military officials. Testing moved from sandbags to live jumps. Volunteer paratroopers strapped into experimental nylon chutes. Each leap a quiet act of trust in chemistry and human ingenuity. Early drops were tense. Observers recorded the behavior of each canopy, the initial inflation, the glide, and the landing. Some tests ended with minor tears or abrupt descents. Others were flawless, demonstrating the fiber's unprecedented potential. Soldiers began to see nylon not as an unknown, but as a symbol of reliability. Meanwhile, DuPont's factories had to transition from experimental production to mass manufacturing. Entire floors were repurposed for the delicate spinning and weaving of nylon. Workers learned to treat the synthetic fibers differently than cotton or silk, understanding that even slight deviations in tension or humidity could compromise a parachute. Supervisors implemented new quality controls, measuring every spool, every weave, every knot. The industrial effort was as much a battlefield as the skies above Europe. Political and military leadership closely monitored progress. Army officers visited Wilmington, inspecting fibers, observing test jumps, and pressing engineers for timelines. They understood the stakes. The U.S. was preparing to enter a global conflict, and every parachute failure could cost lives. DuPont's success would directly influence airborne tactics, supply drops, and the ability of paratroopers to reach enemy lines safely. By mid-1941, the first production-grade nylon parachutes were ready for extended field trials. Each successful jump was a small victory, proof that science and industry could respond to war's demands. These parachutes promised to free the military from dependence on foreign silk, allowing training and combat operations to expand without interruption. But challenges remained. Scaling production further, maintaining consistent quality, and ensuring that soldiers trusted the new material enough to risk their lives from hundreds of feet in the air. The stage was set for nylon's first real test. It was no longer a laboratory experiment. It was a question of survival, strategy, and innovation under the shadow of war. The fibers spun in Wilmington would soon leave the controlled environment of laboratories and factories, descending into battlefields where human lives would depend on them. In the early months of 1941, the people behind nylon parachutes were as vital to the war effort as any soldier on the front lines. Scientists, engineers, and factory workers toiled in near silence, their lives consumed by strands of a golden fiber. Wallace Carruthers, the chief chemist, spent countless hours hunched over microscopes and chemical apparatuses, adjusting polymer formulas with meticulous precision. Every failure weighed on him, not just professionally, but morally. The lives of paratroopers, many of them young and untested, hung on the success of his experiments. On the testing fields, volunteer soldiers faced the unknown. Strapped to prototypes, they leapt from wooden towers or low-flying aircraft. Each descent was a moment of tense anticipation. Would the nylon hold? Would they land safely? Observers, including engineers and military officers, held their breath as chutes unfurled, snapping in the wind or billowing perfectly. Successes were celebrated quietly. Failures were meticulously recorded, analyzed, and corrected. It was a shared human drama. Fear, hope, and determination intertwined in every test jump. Nylon was a breakthrough that redefined the boundaries of textile science. A polyamide polymer, it could be stretched and woven into threads stronger than silk, yet light enough for parachute deployment. The secret lay in its molecular structure. Long chains of repeating units aligned under tension, creating both flexibility and tensile strength. Engineers experimented with spinning techniques, weaving patterns, and thread thickness, balancing durability with weight. But technological innovation was only part of the story. Scaling from laboratory samples to hundreds of thousands of yards of parachute material required precision machinery and an understanding of industrial chemistry few had mastered. Even slight variations in humidity, temperature, or polymer alignment could compromise a parachute's integrity. The challenge was not merely inventing nylon. It was producing it reliably at scale under the urgent pressure of a world at war. The introduction of nylon parachutes transformed military planning. Paratroopers, once limited by unreliable silk chutes, could now train and deploy with confidence. Airborne operations, previously considered risky gambles, became feasible components of strategic planning. Commanders could envision dropping troops behind enemy lines, securing supply routes, or establishing beachheads without the fear of widespread parachute failure. Nylon parachutes also influenced supply logistics. The Army could stockpile thousands of reliable chutes, ensuring continuous training and operational readiness. Each successful deployment meant fewer lives lost during jumps, higher morale among troops, and greater flexibility for planning complex operations. In essence, a strand of synthetic fiber was not just a technological achievement. It was a tactical multiplier, changing the calculus of warfare. As these angles unfolded, it became clear that nylon was more than a product. It was a convergence of human courage, scientific innovation, and battlefield necessity. Engineers, soldiers, and commanders all relied on it, each perspective reinforcing the importance of success. The thread spun in Wilmington carried the weight not just of men descending from the sky, but of an entire nation preparing for war. This growing confidence in nylon would soon be tested on a broader scale, as factories ramped up production and the Army began deploying these parachutes in full operational trials. The stakes had never been higher. DuPont's laboratories had solved the problem of nylon in theory, but the challenge of mass production loomed larger. Factories once dedicated to conventional textiles were transformed into vast, humming cathedrals of machinery. Floors vibrated with the constant whir of spinning wheels, weaving machines, and chemical mixers. Workers, men and women alike, learned to handle nylon threads with almost religious care. Even a slight misalignment in the weave could render a parachute useless. The scale of the operation was unprecedented. Tens of thousands of yards of nylon had to be produced, inspected, and prepared for packing, all under the pressure of impending war. DuPont established rigorous quality control measures, instituting inspections at every stage of production. Supervisors measured tensile strength, elasticity, and thread consistency, while factory floors operated around the clock. Any deviation could compromise a life. The responsibility was immense. Industrial engineers coordinated raw material procurement, chemical processes, and workforce training with military liaisons, creating a seamless production chain. Factories became living entities, their success measured not in profit, but in lives saved and missions enabled. Nylon was no longer just a scientific breakthrough. It was a triumph of industrial organization, a symbol of America's capacity to mobilize for total war. Leadership at DuPont and within the U.S. Army proved decisive in turning innovation into battlefield reality. DuPont executives, recognizing both the commercial and patriotic stakes, allocated resources without hesitation. They shielded Carruthers and his team from bureaucratic delays, allowing scientists to focus entirely on perfecting the fiber. The company's leaders understood that failure was not an option. The first operational parachutes would determine public confidence and, ultimately, soldier survival. On the military side, officers such as members of the Quartermaster Corps oversaw parachute trials with meticulous attention. They set performance benchmarks, analyzed each test jump, and pressed engineers to refine designs. Collaboration between civilian scientists and military strategists became a model of wartime cooperation. Every decision carried weight, from adjusting polymer thickness to selecting parachute cord lengths, because these details could mean the difference between a soldier's life and death. This dual leadership, scientific and military, created a climate of focus and accountability. The combined urgency of national defense and human responsibility drove every choice. Under pressure, both teams learned to adapt, innovate, and execute with precision, turning nylon from a laboratory curiosity into a battlefield-ready tool. While the United States raced to produce nylon, the Axis powers were also seeking technological advantages. Japanese silk remained largely in their control, making parachutes a strategic asset for both sides. German and Japanese forces relied on both conventional and experimental materials for airborne troops, but their innovations did not reach the same industrial scale as the American program. The threat of enemy interception loomed constantly. Had the U.S. continued to depend on imported silk, supply lines could have been cut, leaving soldiers in jeopardy. Nylon represented not just a domestic solution, but a strategic countermeasure, an ability to produce war-critical materials independently. Each parachute descending from an American plane symbolized a subtle but vital edge: self-reliance in technology, the capacity to sustain airborne operations, and the knowledge that enemy control over raw materials would not dictate the war's outcome. The convergence of these angles, industrial scale, decisive leadership, and the ever-present threat of the enemy, demonstrated that nylon parachutes were more than a material innovation. They were a strategic necessity, a testament to human ingenuity under pressure, and a demonstration of what coordination between science, industry, and the military could achieve. The confidence built across these perspectives paved the way for the first large-scale operational deployment. The laboratories, factories, and testing fields had done their work. Now it was time to see nylon's true value in combat. The success of thousands of lives would soon be measured not in laboratory tests, but in the skies over distant battlefields. By the spring of 1942, nylon parachutes had moved beyond laboratories and test fields. The United States had officially entered the war after Pearl Harbor, and the urgency for reliable airborne operations was greater than ever. The first operational deployments were planned carefully, beginning with training exercises designed to simulate combat conditions. On a gray morning at Fort Benning, Georgia, the air was thick with anticipation. Rows of young paratroopers stood at the edge of transport aircraft, each strapped into a nylon parachute for the first time. The fabric glinted faintly in the dawn light, promising a new era of safety and reliability. Officers issued last-minute checks, their hands running over lines, cords, and canopy folds with precision. Nervous energy crackled through the ranks. Every jump carried more than individual risk. It carried the weight of national confidence. The planes climbed steadily, propellers slicing through the morning haze. At 1,000 feet, the jump command were given. Soldiers leapt into the air, and one by one, the nylon chutes unfurled. Observers held their breath as each canopy caught the wind, stretching fully and slowing the descent. There were minor wobbles and gust-driven swings, but no catastrophic failures. Sandbags tested alongside soldiers confirmed the material strength. Engineers and officers exchanged subtle nods. This was working. This successful deployment was more than a training milestone. It demonstrated that the U.S. could now equip paratroopers with a homegrown, reliable material. Airborne tactics could expand, and soldiers could be trained intensively without fear of losing chutes mid-descent. Field reports began to circulate, praising nylon for its durability, lightweight construction, and consistent performance. Soldiers who had once worried about silk's fragility now felt a quiet confidence with every jump. Operational tests quickly scaled. By mid-1942, entire battalions were training with nylon parachutes, practicing mass drops and coordinated landings. Engineers monitored each jump meticulously, analyzing canopy inflation, line tension, and descent patterns. Adjustments were minor but significant. Small changes in cord length or canopy fold improved stability, and the data collected informed every subsequent batch of production. The psychological impact on troops was immediate. Paratroopers began to trust the material, a subtle but vital factor in combat readiness. Trust in equipment is intangible, but it influences morale, precision, and even survival instincts. Nylon parachutes were no longer just fibers. They were a promise that soldiers could rely on when facing the uncertainty of airborne operations. At the same time, DuPont's factories had ramped up production to meet growing military demand. Thousands of parachutes were shipped weekly, arriving at bases across the United States and preparing for overseas deployment. Logistics officers noted the consistency. Nylon parachutes could be folded, packed, and stored with predictable performance. something Silk had never reliably offered. This reliability allowed commanders to plan large-scale airborne operations, confident that their soldiers would reach the ground safely. The first combat-ready tests were scheduled for early missions in the Pacific Theater. Here, the stakes were real. Supply drops, reconnaissance, and troop insertions relied on parachutes functioning perfectly under unpredictable conditions. Strong winds, heavy equipment, and hostile territory. Nylon's lightweight strength gave paratroopers the ability to descend smoothly even with full gear, while the Army's confidence in the material allowed planners to attempt maneuvers that would have been unthinkable with silk. By the summer of 1942, nylon parachutes had passed every training benchmark. Soldiers, engineers, and commanders alike recognized the tangible difference. Fewer accidents, predictable deployments, and an expanded operational envelope. The war, still unfolding in Europe and the Pacific, had just gained a new tool. One synthetic fiber, born from laboratory ingenuity and industrial ambition, was beginning to save lives. And yet, the true test of nylon parachutes was still ahead. Large-scale deployments in real combat conditions would determine whether this innovation could withstand the chaos of war itself. By late 1942, nylon parachutes were no longer confined to training fields. They were entering the crucible of combat. The first major airborne operations using nylon came during the Solomon Islands campaign in the Pacific. Paratroopers and supply teams faced jungles, rocky terrain, and unpredictable weather. The stakes were immense. Failure meant injury, death, and compromised missions. At dawn, transport planes roared down improvised airstrips. Soldiers, now veterans of rigorous training with nylon chutes, tightened straps, and checked lines. The fabric gleamed faintly, a silent promise of safety amid uncertainty. Commanders counted heads, gave final instructions, and the troops leapt. One by one, the nylon canopies inflated, suspending men gracefully above the dense foliage. Where silk might have torn, nylon held firm. Where silk might have collapsed under wet conditions, nylon resisted moisture, maintaining its structure. Soldiers landed, shaken but uninjured, ready to advance in a hostile territory. Supply drops were equally transformative. Ammunition, medical kits, and communications equipment could be lowered via nylon parachutes without fear of destruction. Packages landed intact, immediately usable by troops on the ground. The tactical advantage was clear. The military could sustain operations in areas previously unreachable due to logistical constraints. In the Pacific, where islands were isolated and terrain unforgiving, this capability was decisive. Reports from the field confirmed the material's reliability. A battalion commander wrote, "Every jump went as planned. Nylon performed beyond expectation. Our men landed confident, and our equipment arrived intact." Engineers and military analysts studied each deployment, refining design and packing methods. Lessons learned in the jungles of the Pacific would influence airborne strategies in Europe and North Africa. Nylon's success was not limited to the Pacific. In the European theater, paratroopers preparing for Operation Torch, the Allied landings in North Africa, also relied on nylon. The larger scale of these operations tested mass deployment under pressure. Hundreds of soldiers jumped from C-47 transports, often in tight formations, each canopy deploying within seconds of the next. Commanders watched anxiously from the air and ground. And again, Nylon delivered. Canopies held, cords stretched and rebounded, and soldiers reached the ground in formation, ready to secure key objectives. The material's resilience was particularly notable in extreme conditions. Rain-soaked drops, sudden gusts, and abrupt canopy openings tested the fiber to its limits. Yet nylon resisted tearing, stretched to absorb shock, and retained its shape. These characteristics directly reduced injuries and fatalities compared to the previous silk parachutes, allowing paratroopers to focus on their mission rather than the reliability of their equipment. DuPont's industrial effort mirrored these operational successes. Factories worked relentlessly, producing parachutes at a rate unmatched in history. Weekly shipments grew into tens of thousands of units. Quality control ensured every chute met precise specifications. For the first time, the military could plan operations without the constant worry of parachute failure, a seemingly small factor with massive strategic consequences. The psychological impact on soldiers cannot be overstated. Confidence in their equipment translated into sharper focus, quicker reactions, and greater cohesion during jumps. Nylon parachutes had shifted the human element of warfare. Paratroopers no longer leapt with fear, but with trust in their gear. Engineers and scientists, observing the results from thousands of miles away, finally witnessed the tangible proof of their labor. Lives saved, missions enabled, and a strategic advantage solidified. By the end of 1942, nylon had proven itself in both training and combat. The fiber had moved from experimental laboratory material to battlefield necessity, altering the landscape of airborne warfare. It was a triumph of science, industry, and leadership converging under the pressures of global conflict. The success of nylon parachutes not only saved lives but reshaped military planning. Commanders could now envision more ambitious airborne operations, confident that each jump carried soldiers safely to the ground. What had begun as strands of synthetic polymer in Wilmington, Delaware, had become a lifeline in the skies of the Pacific and Europe, an innovation that changed the course of operations, and in small but vital ways, the course of the war itself. The immediate impact of nylon parachutes was profound. Paratroopers, once limited by fragile silk, now landed with a reliability that fundamentally changed military operations. Reports from the Pacific and European theaters were unanimous. Nylon parachutes were stronger, lighter, and more durable than anything previously used. Injuries from failed canopies declined sharply. Commanders, once cautious about large-scale airborne maneuvers, could now deploy troops with unprecedented confidence. The material had transformed both training and combat readiness. Supply chains also benefited. Nylon's domestic production eliminated reliance on imported silk, which had been increasingly uncertain due to Japanese control of the Pacific and German naval blockades. Entire battalions could be equipped without waiting months for shipments from overseas. Logistics officers began to plan large-scale drops of troops and equipment, knowing that nylon could withstand the weight and strain. Ammunition, radios, medical supplies, and food parcels all descended intact to frontline units, sustaining operations in previously inaccessible areas. The Army's training programs expanded. At bases from Fort Benning to Camp Mackle, paratroopers conducted repeated jumps with confidence. Exercises that had once been limited to a handful of volunteers now involve entire regiments. Each successful landing reinforced the trust soldiers placed in their equipment. Commanders observed that morale improved markedly. Men who had once hesitated before stepping from the aircraft now leapt with resolve, knowing their lives were protected by a synthetic innovation born of American ingenuity. Beyond the battlefield, nylon parachutes sparked a broader industrial and technological transformation. DuPont's success became a case study in the power of coordinated civilian and military effort. Laboratories, factories, and testing grounds operated in unison, demonstrating that scientific research could meet the urgent needs of war. The fiber itself was a marvel, resilient under extreme conditions, lightweight, and consistent in quality. It was a testament to years of research, experimentation, and meticulous quality control. The first official evaluations underscored the scale of the achievement. Army inspectors documented thousands of successful jumps with nylon parachutes, noting a dramatic reduction in equipment failure compared to silk. Engineers recorded consistent tensile strength, predictable canopy inflation, and reliable cord performance. In letters and reports, officers praised the material's dependability. One battalion commander wrote, "Nylon parachutes have exceeded our expectations. We trust them with our lives." Such endorsements reflected both the technological breakthrough and the human confidence it inspired. At the same time, DuPont's workforce took pride in the tangible results of their labor. Factory floors that once hummed with experimental tests now produced thousands of parachutes weekly. Workers understood that each roll of nylon, each carefully woven canopy, could save a life thousands of miles away. Their efforts bridged the gap between laboratory science and the realities of global warfare, proving that industrial dedication could have immediate, life-saving consequences on the battlefield. The nylon parachute also influenced tactical thinking. Commanders could now consider airborne assaults and operations that had previously been deemed too risky. Coordinated drops behind enemy lines became feasible. Supply missions could penetrate hostile territory, and paratroopers gained a new edge in mobility. Nylon had not just solved the technical problem. It had reshaped strategy, enabling missions that were impossible just months earlier. And yet, while the immediate results were transformative, the story of nylon parachutes was only beginning. Their success set the stage for long-term changes in industry, military doctrine, and the lives of the soldiers who depended on them. The full scope of these consequences would unfold in the months and years to come, marking nylon as one of the defining innovations of the war. As the war progressed, the impact of nylon parachutes extended far beyond individual jumps. By 1943, the material had become integral to the U.S. military's airborne and logistical operations. Entire divisions of paratroopers relied on nylon, and supply drops that once carried high risk now reached their targets intact, often in hostile territory. The reliability of nylon allowed for more complex operations, coordinated assaults, large-scale drops behind enemy lines, and rapid reinforcement of isolated units. The fiber had effectively expanded the tactical possibilities of modern warfare. Nylon's influence was not limited to combat performance. The industrial machinery and production techniques developed to manufacture parachutes at scale became a blueprint for wartime manufacturing. DuPont's ability to coordinate chemical processes, weaving technologies, and quality control under tight deadlines demonstrated that civilian industry could meet the unprecedented demands of total war. Lessons learned in these factories influenced the production of countless other military materials, from ropes and cargo nets to uniforms and equipment straps. In a way, nylon parachutes served as a template for mass-producing reliable, high-quality materials critical to the war effort. The material's success also reshaped perceptions of synthetic fibers. Before the war, nylon was considered a novelty, a laboratory curiosity with potential for consumer products like stockings. Its battlefield performance proved that synthetic polymers could exceed natural materials in strength and durability. After 1945, this credibility allowed nylon to dominate textiles worldwide. Clothing, tents, ropes, and industrial fabrics increasingly relied on the same fibers that had saved soldiers' lives. Nylon had become both a technological and cultural symbol of American ingenuity. The human element of the aftermath cannot be overlooked. Soldiers who had once feared parachute failure now trusted nylon completely, and their confidence reshaped training, combat readiness, and morale. Engineers and factory workers, many of whom had never seen a battlefield, could witness tangible proof of their work's impact. Every successful jump was a reminder that science, industry, and human determination could converge to save lives in even the most chaotic conditions. Strategically, nylon parachutes altered the trajectory of airborne operations. Operations such as D-Day in 1944 benefited from the U.S. military's ability to deploy thousands of paratroopers with confidence in their equipment. Supply drops could sustain troops behind enemy lines, enabling missions that would have been impossible without reliable synthetic materials. Nylon had not only solved the logistical problem, it had become a force multiplier, allowing the United States to project power more effectively across distant theaters of war. Finally, nylon parachutes left a lasting legacy in industrial-military collaboration. The partnership between DuPont, the U.S. Army, and the scientists who pioneered polymer chemistry became a model for future innovations. It demonstrated that rapid scientific advancement, aligned with industrial capability and military necessity, could create solutions that were both practical and life-saving. In essence, the nylon parachute became a symbol of what America could achieve when ingenuity met urgency. By the time World War II ended, nylon parachutes had saved countless lives, transformed airborne strategy, and laid the groundwork for a post-war era dominated by synthetic fibers. What had begun as fragile strands in a Wilmington laboratory had reshaped military tactics, industrial production, and human trust in technology. The story of nylon's triumph in war naturally leads to reflection, a moment to consider not just the lives it saved, but the lessons it offers about human innovation, the fusion of science and industry, and the courage to leap into the unknown. Nylon parachutes were more than a technological breakthrough. They were a testament to human ingenuity under pressure. In the laboratories of Wilmington, scientists had transformed fragile strands of polymer into lifelines. In factories across the United States, workers spun, wove, and inspected those fibers with relentless care, knowing that each roll could determine the fate of a soldier hundreds of miles away. And in the skies over the Pacific and Europe, paratroopers leapt with trust in a material that had been created for them, one thread at a time. The story of nylon highlights a truth about war. Victory is shaped not only by strategy and firepower, but by innovation, industry, and the quiet courage of those behind the scenes. A single synthetic fiber, lighter, stronger, more reliable than silk, shifted the balance of life and death in airborne operations. It saved lives, enabled audacious maneuvers, and gave commanders confidence to push the boundaries of what was possible in combat. Yet the legacy of nylon extends beyond the battlefield. The fiber's success demonstrated the potential of science and industry working in unison, setting a precedent for future technological innovation. It reshaped civilian life after the war, from clothing to infrastructure, and left a lasting imprint on global industry. But above all, it reminds us that even in the darkest times, human creativity and determination can produce solutions that protect, empower, and inspire. In the quiet moments between jumps, tests, and deployments, nylon parachutes stood as silent witnesses to courage, both on the ground and in the laboratories. They embodied a promise that when necessity demands, humans will invent, adapt, and rise to meet the challenge. From fragile strands of polymer to life-saving tools in the sky, nylon parachutes became a symbol of hope, resilience, and the power of ingenuity. And so, as soldiers touched the earth safely and engineers watched from afar, the lesson endured. Innovation, when combined with dedication and purpose, can change the course of history.